Board. All right. I'm going to, you might need to grab one on the bottom because the ones on the top are still charging. Okay. Okay. All right. Thank you. Okay. So let's do a few notes based on what we've already done, some of the stuff we've already done. So we're going to do some notes and then we're going to come back to that longer worksheet and work some more on that one. And you guys out there tell me if the screen is too far to your left or right, because I've been having that problem today. It looks fine on my screen, but it doesn't look good on your, back here. So if you can't see something, let me know. I'm going to try to get that working. All right. So everything we've done in this class sort of relates back to things like force. And so today we're going to look at forces and energy and the idea of work. So when you do this at your house, you go home and your mom says, well, I need you to do some housework, like clean up your room or take out the trash or pick up the stuff out of the floor or do your own laundry or whatever your parent chooses to do on that, right? And so you understand what the word work means. It's an activity that you do or something you perform or something you get done. We talk a lot about having schoolwork, and schoolwork is papers and assignments and worksheets and practice problems and things like that. Reading maybe, or watching videos this year. So work is going to be a word that we use a lot in our everyday language, but it's not going to be the same exact meaning in physics because we have to be a little bit more specific than just do something. So let's start with what we had: two kinds of energy. And so when we talk about work requires a force and the object moving through some distance. In the same direction as the force. So it's force. Work is force times distance as our formula. W equals FD. All right. So probably sometime in your life before you got to my classroom, you were told when they ask you to define energy, you were probably told something like this: energy is the ability to do work. So what does that mean? Work is the transfer of energy. So we talked about the food. We'll pick on Parker today because she's eating a snack back there. Well, not right this second, but it's all good. So she's got a snack. That snack food, the food she's eating, is currently chemical stored energy. It's potential energy. There's energy stored in the food. It's chemical energy because of the materials that make up the food. And so when she eats it, her body goes through a digestive process and it changes the food from food into broken down nutrients that travel through our bloodstream and help us have energy and movement. That transfer of energy from being stored chemical potential to usable chemical energy in your body and electrical energy. I don't know if you realize this, but your whole body runs on electricity. Everything you do, your body runs on electricity. And so these electrical signals, that chemical energy that was stored in the food, becomes electrical energy and chemical moving kinetic energy, usable energy. We call that transfer, when it goes from chemical to electrical, work. Or we call it from potential to kinetic, is work. So when you change your type or form of energy, we call that transfer work. So if you have a savings account and a savings account and a checking account at your bank, when you take money out of savings and put it in checking, like I had to do this week because I'm getting a fence replaced. Yay for homeowners insurance. But the things you have to do. So I transferred from a stored money to a usable money. That would be work. Here's where it gets a little upsetting. The work has to be in that same direction piece is what's going to cause us a little bit of grief in physics sometimes. This same direction piece can be tricky on us. And so since Nick saw me at the gym the other morning, I slept in this morning. Since Nick saw me at the gym the other morning, I don't think he saw me doing deadlifts. But deadlifts, you pick up a barbell. It's on the ground, right? And you squat down and you pick it up to hip high, waist high.
How much were you lifting?
Yep. You got it. And so deadlifts, I pick it up. What if I was to rack it? Meaning that I would pick up the weight and then I'd take a step forward and put it on the rack. And then I'd let go. Have I done work when I moved forward?
Yes, you have.
In English, you would say yes. In physics, the answer is actually no. Why? Okay. Which way is the force that I'm applying on the barbell? I'm holding the barbell up. Which way did I move? Those are not in the same direction. Not in the same direction. So picking it up and walking it forward, my muscles tell me I'm doing work. My body tells me I'm doing work. I'm doing something, but I'm not doing work in a physics sense. Now, when I picked up the barbell, did I do work? Yeah. Yes, because my force was up and the barbell moved up. If I then put the barbell back down, have I done work? Yeah. Yes, because I pulled up, but the barbell went down, but they're in that same line of action or the same axis, if you will. What about if we were to go to Siegel High School, which is now closed, as you probably have heard? Them in Oakland and Riverdale, and just a matter of time, maybe. I hope not. I hope everybody doesn't get this. But you have to have a certain amount of people get it, right, before we can get the contagious part to die out a little bit. So if we went to Siegel and there was a fire drill and I was on the second floor, first of all, that's not a good place to be if there's a fire drill. Because if you're on the second floor, you have to wait for all the people on the first floor to get out of the way so that you can get out of the building. Or alternatively, you can jump out the windows. But their windows are like our windows, which means you can't break them very easily. We can break those. A desk would probably do it. but let's not test that hypothesis. Right? So those windows are pretty thick. We don't have a handle that would help us get out. So if we're on the second floor, we're waiting for the people on the first floor to get out, and then we can get down. Not unlike if you go to a sporting event, you know, those things we used to be able to go to, or like a concert, another thing we used to be able to go to. You may have heard of those. You may not have experienced them. It's been a long time. But if you're in there, if you're at the top of something, you have to run down the stairs. So when I'm running down the stairs, am I doing work or not?
No.
Well, the part that's moving forward, right, because you're stepping down, the forward part of your motion is not work, but the up and down part of your motion would be work. So when I carry the barbell forward, if I carry the barbell this way, what's doing work in that case? Well, my feet are doing the work against the earth. I am pushing on the earth that way so that I will get pushed this way. So it's not my up and down force from my arms that's doing the work. It's the frictional force with the floor, because I'm pushing backwards so that I can carry the barbell forward. Okay. So we're going to look at work. It's going to be just one part of our piece here, one part of our puzzle piece, but it's going to be the piece that if the force doesn't go in the same direction, along the same line of action, then we haven't done work. So, yeah. So, remember that force and distance need to be along the same line. The same line for work to be done. So let's say let's imagine for ourselves a swimming pool in the summer. Maybe that'll make us feel warmer if we imagine a swimming pool in the summer. Maybe it won't. And it's a swimming pool like at Nashville Shores.
I can't swim.
Say again?
I can't swim.
Oh, then you shouldn't be getting this, my friend. Okay, so let's say that our swimming pool, you can or you can't. Depends on what you think you're going to need to do to remember. Let's make it with a slide. So we have a slide, little platform up here, and then you can slide off into the water like at Nashville Shores, just to do something. All right, so let's look at if we are right here. We're going to make a happy little purple person. Yay. Sliding down the slide. I'm pretty good at stick figures. Other pictures not good at, but stick figures I've gotten kind of good at over the years. So what forces act on this stick person while they're sliding down the slide? Gravity, and it's going to point where? Down. How about I could draw a straight line? That would be helpful. Let's try that again. There we go. Gravity's down. Friction. Which way would friction point? Straight left or up and left? If we're on a slide, right, if we zoom in on that part, we would have our person here. So yes, the surface won't be exactly level with the ground, right? It's going to be slanted a little bit. So the friction is always going to point back and up the plane. So wherever you're going, friction will point directly behind you. So for this moment, let's just say it's going to point somehow over this way. We won't get excited and have swirlies and loops and bumps and whatever. And
Hey,
then
Miss
what
Joy.
else do we have acting?
Miss Joy,
Yes.
You're cutting in and out. Can you like mess with the volume or something? I don't know.
Okay. I did turn it up, but we're having internet problems still at school.
Yeah, the Wi-Fi's some dog.
Yes, well, somebody lost their job evidently this week for
Yeah,
that.
it's some dog shit.
Easy. All right, so force of friction, force gravity. And so we don't have another force pulling us down because gravity pulls us down. And since the thing is sloped, we slide down the slope instead of falling straight down. So if I wanted to find the work done, and maybe if it just helps if I have my mask off for a little bit. If I want to find the work done, the frictional work will need to use the distance that you go down the slide. So this one would need distance down the slide. Because the frictional force works along the surface of the slide. Since the frictional force works along the surface of the slide, the distance you measure should be the distance along the slide. What about the force due to gravity, though? Which distance would I measure to get the force due to gravity? How would it have to measure? Have to measure from here straight down. Because gravitational force acts straight down, so I would take the distance straight down to find the work. And the work in this case, we would be changing potential energy here to kinetic energy here. That would be our transfer. I'll wait here and see if there's any questions as we talk through that. Okay, what about this? Actually, let me do a little better than that. Let's do this.
Hey, Miss Joy,
Yes.
do you know if we're gonna get out of school anytime soon?
No, sir. I haven't heard anything about that. Everybody's making guesses, but I haven't heard anything about that.
What do you think?
I just don't have any idea. I really don't. If I felt like I had a clue why they make the decisions they make before, I might guess, but I feel like we're just kind of putting out little fires.
Yeah, me too.
I'm not judging anybody on that. This is what it is. So
I think it's pathetic.
well, you are certainly entitled to your opinion on that. Okay, so we're gonna do little Johnny with his backpack. Yes. Huh? Oh yeah.
Wait, your legs don't do that? No.
Maybe he's got a broken leg, man. Don't be so judgmental.
Yeah.
Okay. So if he's walking this way, what forces are acting on the backpack? What forces act on the backpack?
That works at the person holding up the backpack because you have to hold it up or it'll fall.
Okay, so there's going to be a force tension from the straps. So either one force or two forces, because when you pull your backpack on, most of you I know just pull one over one shoulder, right? But it's still like a tension because it's a rope or a strap that's holding the backpack up.
Lunchtime.
You lift up the floor force for him moving. So gravity too, right? Because it's pulling down. That ain't gravity, that's where I'm going.
Hang on just a second. since I don't know who it is. There you go. Now, as I was saying, if you're not one to make a noise, put your name on the sign. It's real easy. All right, so force tension, force gravity.
I'm gonna say, things right now.
Hang on just a second. They're not showing over there. Okay. So when the person walks forward and the backpack's on their back, which one of these forces or either of these forces pulls the backpack along with you?
Yeah, one at the top.
So you have tension over your shoulders, right? But the strap also comes down the front of your chest. So you also have a tension force because this is sort of like a seat belt in that it also attaches to your chest. So the top one and bottom one don't do the work when you move forward, but the one that is in front of your chest. So when I take my backpack, got visual aids. So if I take my backpack, ooh, not zipped up, and I put it like this, I have two forces of tension. One force of tension holds the backpack up to keep it from sliding down. The other force is the part that's attached to my shoulder and points out this direction. And so when I move forward, that would be the force doing the work. If I then take my backpack off and lay it down, now the up and down forces will do the work. I'll do that again. Okay, so gonna stop right there. I'm gonna open this up, so I'm gonna stop share because I'm gonna go back to our worksheet now. Let's see. Yeah, those are, it's fine. So I'm gonna pause for, all right, so let's go back to our worksheet. And I do post these, I will post these on my website, on my YouTube. So let's look at what's going on here. Let's look at number 1. I'm gonna make sure that I don't. I'm gonna share my screen back with you guys so you can see the one I'm working on. We're gonna do number 1. So consider the falling motion of the ball in the following 2 frictionless situations. For each situation, indicate the forces doing work on the ball and whether the energy is conserved and not. Okay, so do we have forces doing work when the ball falls off this pillar and it falls to the ground? Is there work being done? Yes. What force is doing the work?
KE.
It's kinetic energy that we're getting, yes. We are getting kinetic energy from potential, but the force name would be gravity. So right before it hits the ground, what's going to be its potential energy right barely above the ground? 0. What's its kinetic energy going to be then? It's going to be 100 because we had 100 to start with, so we have 100 to end with. It's okay. Sometimes you overlook a 0 or you add a 0. It happens. I'm very much a fan of giving people mercy rather than justice most of the time. Sometimes you have to do justice, though. That's the kick you out of class. Yeah, I did it the last time when they were putting up Dr. Justice misspelled and asking Nick if he was watching. You probably didn't see me do that, but I did.
You did kick him out?
Yeah, after a little while. All right, so is our energy conserved?
Yes.
Yes, energy is going to be conserved. Okay? The only time energy is not conserved is with friction. No friction, no air resistance, so no energy change. So our equation would be kinetic energy plus potential energy. We don't have work done because gravity's in our situation. We have the earth, we have the ball, that's our system. So let's talk about that for just a second. What is our system here? What objects are part of our system? The earth, because that's where gravity comes from, and the ball. Those would be the two objects in my system. So the earth and the ball. So I don't have any outside forces doing work because both of those are in my system. Earth's in my system, so I have gravity. And really the only one you have to worry about is friction. Friction always causes you to gain or lose energy. It actually always causes you to lose energy. The system always loses energy and it turns into heat. So friction, as our side note over here, friction is an energy loss. An energy loss, and it takes energy. Well, let's hang on to that. I'll talk about that one later when we're more on that. Yeah, I probably shouldn't toss. I probably caught somebody I shouldn't have on that last one, but sometimes it's hard to get the right. You know, you toss 3 or 4 people, you're going to get somebody you shouldn't have. But when I don't know what your name is, so that I can't tell who's on the doing it, these are the breaks. All right, so, and I really can't deal with this today. I just can't deal with that kind of thing. All right, so friction is energy lost. And what happens with friction typically is it takes your energy and turns it into heat. So for example, my classroom when I got here this morning was 67 degrees. And I was told that that was perfectly normal and that was within tolerances. That was an okay temperature to be. And I said, well, not so much, really. My kids are freezing. It's hard to focus. So while I'm waiting for them to turn on the actual heater, I'm doing this a lot, right? Why do I do that? Because that friction turns into heat for my hands. So I'm taking kinetic energy and turning it into heat. Friction removes the energy from my system, which in this case would be me, and turns it into heat energy. All right. So let's look at we did these, right? Let's look at number 4. We haven't done number 4 yet. Second page. So it's the big packet. We're now on the second page. Look at it, number 4. And I'm going to zoom this up a little bit. But hopefully, that's showing on the screen. Okay, yeah, that's basically showing on the screen. Yes, sir. Oh, you just thinking? You want a question? Okay, it's fine. It's fine. I just didn't want to miss one. All right, so a 2 kilogram mass ball moving 2 meters per second is rolling towards an inclined plane. It eventually rolls up the hill to a position near the top where it is momentarily stopped prior to rolling back down. So we've got, it's going to roll up the hill, stop, and then it's going to roll back down the hill. So construct a bar chart. Okay. So what kind of energy does the ball have when we start? Does it have kinetic? Because it is. So at point A, it has kinetic energy because it's not stopped. It's moving. So we got moving energy. So we would have some amount of kinetic energy. I don't care how tall you make the bar. Okay. Doesn't matter to me. There's my bar. Do I have potential energy at point A? Because I don't have any potential energy at point A because I'm on the ground. So there's 0 potential energy. So what is my total energy? It is all due to kinetic. So whatever size you made the first bar, you better make the second bar for TME the same size. So if Abigail wants to make it 2 bars tall both times, that's fine. If Hannah wants to make it 3 bars, that's fine. Just as long as you're consistent. Now, what happens when we get to point B?
0.
0 what?
Kinetic.
0 kinetic energy because we have no speed. We're not moving. So now I'm going to switch over because I have, since we're Blackman, we'll go with orange. Now we have all potential. Yes, sir. Yes, sir, you may. So we have 0 kinetic this time because we stopped moving, and we have all our energy is potential. And so our total mechanical energy, we are still conserving energy because there was no friction in our problem. All right. So now we're going to practice with the math piece. This side is your starting energy. Just right below number 4. And this is our final energy. And we're going to figure out which terms we keep and which ones we don't. So based on our bar graph, what kind of energy did we have at the beginning? We had kinetic. Which one of these statements is kinetic? The one that has speed in it, velocity in it, right? So this is my kinetic energy. This is potential energy, and I don't have any of that. This is work. I don't have any of that. Questions? Say that one more time, London. So now what we're going to have on this equation is 1/2. What's our mass? 2. And our velocity was also 2. So that gets the left side for us. Now what do we have at the end? What's our final energy? All potential, so we mark out the, there's no kinetic. We're finding the height. Because they ask us to determine the height. Ooh, I did not do a good job of drawing that. All good. We'll figure it out. There you go. So we know that the mass is 2. We know that gravity is still going to be 10, but we don't know the height. That's the piece we're solving for. So what do we get for the left-hand side? 1/2 of 2 is 1, and 2 squared is 4. So we get 1 times 4 has to equal 20 HF. So what does HF equal? 2/10, yes, but also
Isn't that -5?
1/5.
Okay.
Why did I not make gravity negative here?
Because gravity can't be negative.
Well, in this case, the ball was going up, so I'm measuring its height, not its, I'm using the downward motion to figure it out, but the ball actually moved up. And it was slowed down, so it was being pulled down, but it moved up. So we get 1/5 or 0.2. And what's our unit for height? What would you be measuring height in?
Meter?
In the English system, be feet, and in this system, it would be
Meter.
meters. Okay, now let me, whoops. There's some chats going on over here. See what we got. Oh, okay. Yeah, the connections are sketchy at school too. Sorry about that. I just didn't want to miss a question. How you guys doing out there right now?
Good.
My physical people doing okay?
Yeah.
Okay. So let's do one more. And then I'm going to have you, I want you to work the front and back of the first page and the front of the second page. Okay, so the first 3 pages, basically. That's what we're going to work on for Monday. And then lab stuff we're going to work on too, if we have time. So let's do this one about ranking things, number 7 and 8. Let's do number 8. We can do 8 and 9, and then you can do the other 2. All right, so they ask you to put a letter, and we're going to go from smallest kinetic energy to largest kinetic energy, and we'll put equals or greater than or less than symbols in our blanks. So you've probably, I don't think we've done any of these much like this in here. Have we this year? I didn't remember doing any like this. So we're going to do number 8 and number 9. Now, number 8 says smallest potential energy. Number 9 is smallest kinetic energy. So which one of these locations, A, B, C, D, or E, has the smallest amount of potential energy? Why is it B, Nick? So then the next one will be greater than that. So the one that's on the ground has the least potential energy. Who would be the next?
E.
Why E? It's the second lowest. So how are we ranking these? Potential energy goes from least to greatest when you go from where to where? Lowest to highest position. So then my next one will be D. My next one will be C. And my last one will be A, because A is the highest. Yep.
Wait.
How would we,
Next question.
how would we know when to use the equal sign?
What was that?
How would we know to use the equal sign?
Because none of them are at the same height.
So do we not use it at all?
There were no equals ones on this one, okay? There could be on some of the other ones, but not this one. Okay, number 9 asks us to do the same thing, but do kinetic energy. All right, so kinetic energy we're going to have to think about because it's our speed. Where would our roller coaster be going fastest?
A.
At the bottom of the first hill. Why? Because as you come down the hill, your potential energy is turning into kinetic energy. So you're going to have the most kinetic energy down there at that bottom of the steepest hill. So this would be the biggest, nope, this one goes from smallest to largest. So our biggest one this time is B. What's our smallest one? And I think Romel said that, or somebody on that side said it, A. A is the least amount of kinetic because it's the most amount of potential.
So it's like the opposite of those.
Right. Because what happens is I go, like, if I'm riding a roller coaster, we get really, really, really slow at that top, right? They're pulling you up with a chain of some sort on the old fashioned kind that go up and down. They pull you up with a chain and you get to the top and you almost stop briefly. You're still moving a little bit, but they pull that over in that next little bit, and then you start, gravity just naturally pulls you down. The fastest you go is at the bottom of the first big hill. But then when you start to do a loop, you start to slow down as you move up. So as we move to C, as we're moving to C this way, we're going to be slowing down. And so which one is, this one has a lot more potential. So it has more potential, right? Less kinetic. So which one will it get paired with? It'll be the next least or the next most. If the potential energy goes this way, the kinetic energy will go that way. Okay? Potential decreasing, excuse me, that's not a helpful way to represent that, sorry. If your potential energy is, let's do it like this. As your potential energy goes down, your kinetic energy goes up. So
C is the second lowest.
So C would be the second lowest for kinetic. Then
D,
D,
and E.
then E. So if you'll notice, the kinetic and the potential are exactly opposite of one another. Because when potential goes up, kinetic goes down. So say that again. Okay, so what's true about the total energy? Nick thinks they're all equal.
Yes, I do too. A and B are definitely.
Yeah, because all the potential turns into all kinetic. Do we have friction?
No.
Since we don't have friction, no energy is lost. All of it has to stay inside. So the total energy will be, you can write it in any order because they're all equal. Nobody's bigger than anybody else. Sorry, my sinus is all of a sudden draining. Probably because the near miss on the crying. So your tears have cortisol in them. It's a stress hormone. It's not good for you. It's kind of poisonous. So your body gets them out here before they get up into that chemical gets up into your brain. So by crying, you get a chemical that is dangerous out of your body. Yeah.
Wait, so if you drank a bunch of tears, it would kill you?
Maybe you like salt water. Yeah, if you drank a bunch, you'd be putting it in your bloodstream and your blood would clean it out too. So yeah.
So it wouldn't kill you?
No.
What happened?
This is how I know who's listening in class and who isn't.
Crying kills. Wait, crying kills you? Yeah.
No,
So we gotta-
it won't kill you, but it creates bad reactions because it's cortisol's a chemical that's a poison.
Bad stuff out of your body.
Yep.
It's like we're about to
So
go
when you're
down.
stressed, your body creates cortisol, right? Any kind of stress.
Oh, I got a bunch of that in here.
And then your body has to figure out a way to get rid of it. And if it doesn't, you get bad things happen. And that's why stress acts so differently for everybody. So like Josh might have stomach cramps when he's really, really stressed out. But Patrick might not be able to sleep even if he really needs to. Or maybe Nick eats a lot when he's stressed out and Jacob doesn't eat at all. It's kind of because of those chemical processes. Yeah. So anyway, back to physics.
We're about to get good. We'll think about the lunch.
5 minutes.
Yes. So we're just going to do one of these because I think we've got the hang of this. So how would I figure out the total energy in this question right here? Number 10, I'm going to zoom it down just a little bit. Where can I figure out what the total energy is?
Yeah, they can't eat right there. Let's see. You add them together.
Okay, so down here, you add these two together to get 40,000, right? Because you know both of them. So what does that mean about the kinetic energy at point E? What would it have to be?
3,500. Same thing, huh?
If it's the same thing, I want the 35,000 in my bank account, not the 3,500. I'm teasing you, man. Okay, so let's do a bar chart for these. So what would be true about the total mechanical energy at E?
It's all the way full.
It's all the way full. Okay. What about the other spots?
What do you mean? Halfway.
So potential energy would be
No friction, so the total energy column will be full the whole time. Won't change. So do we have more potential or more kinetic at point E?
more kinetic.
Okay, so I'm going to make kinetic 3 bars, and I'm going to make potential 1 bar.
Why?
Say that louder.
There's more kinetic than there is potential.
There's more kinetic than there is potential because at E we have 35,000 kinetic, but we only have 5,000 potential. So I'm going to make the bar for potential short, and I'm going to make the bar for kinetic tall, but they still have to add up to all 4 bars. Okay? 1, 2, 3, 4, 5. Sorry, I can't count. 5 bars. So then I need a 4 and a 1 or a 3 and a 2. So if Emma puts 3 and 2, that's fine. If Lauren puts 4 and 1, that's fine. Either way is fine with me. Okay. All right. So now we're fixing to go to lunch, and we come back at 1:13 for DLRTI. So you guys are welcome to come back after lunch if you want.
Do we have to?
You know, you have to. Good try, London. Well played. But they have a choice. Thank you, sir. And if you have that first energy worksheet ready to turn in, just plop it in the folder. And I will put the folder, let's see, where can we put it? We'll put it right there in that middle table. Close everyone. And when we come back, I'm going to hand back this whole big stack of papers that got graded. Let's see, I need to say something to.
Hey, Patrick. How's the weather? I like the prediction.
Here you go. Come back this way a little bit. Thank you. Yes,
How are you?
I'm doing okay. It's not been a good morning, but it's okay. We will survive that too. Close that. You know, sometimes it's like your iPad or your iTunes knows what you need because it played a whole bunch of sad songs, and then right when y'all came in, it put on "I'm Sexy and I Know It." That song is just wrong in so many ways. So it's hysterical. You remember the guy that used to paint his belly at the hockey games? They'd play "Sexy and I Know It," and the big guy, he passed away a couple of years ago, but he'd paint his belly, and so he'd be doing the shimmy to get the crowd to cheer for him to pull his shirt up because he painted something on his belly. You know, like it was pretty impressive. It was serious, like artwork. But that's what they always played because he was like 6'4" and huge, just a big, huge guy. It was so funny.
Did you look at that? Okay,
I will. No, I haven't had time to yet.
Okay, good.
Okay.
Well, I'll see you later.
All righty. Y'all have a good lunch. Okay. Welcome back.
Wonderful, son.
Hi, Jacob. Thank you for the note. I really appreciate it. Did you ever get an invitation to the Discord server?
Yeah. I'm
Okay.
in it.
Because we're going to meet next Tuesday. No, not next Tuesday. The next Tuesday. The last week we have a next meeting.
Okay. Okay, we're just-
So I think that's the 15th.
Friday's the 18th. You said Tuesday, right?
Yep.
So 17th is Thursday. Yeah.
That's it'd be the 15th.
Let me make sure I'm in the right.
From 4 to 5, basically.
Um. Um. I do.
Okay.
Actually not, which is surprising. Yeah. Apparently, I'm actually not in it. But I was.
Oh, okay.
I did send a message to him. Like,
Okay. Well, you can send one to me if you need to, because I can send you a link as well.
Where's my wallet, keys, and phone?
It just doesn't work very well at school.
Hmm?
It doesn't work very well at school.
oh, I wasn't in school with them.
Yeah.
Yeah.
Okay, so let's review a little bit of note things. Okay, so that was yesterday.
Who? No, who asked?
And this one.
You started it. I just finished it.
It's like you guys are brothers in class. Irritable siblings.
Or he's just regularly irritable. I hope that's right. I think that's right.
Calculations. Okay, now.
Wait, does this have to equal 40,000 the whole time?
Did you lose any energy anywhere?
So it has to equal 40,000.
Every time. Yep. Yep, it does. Okay, let's. No, I need. Sheep monkey, come on, YouTube. Trying to get that all added to the YouTube. Publish that. Okay. Share. Okay. So I'm going to minimize this. Close that.
How do you know if you blush you don't use them?
You can't hear anything.
Your heart hurts really bad.
It hurts really, really, really badly.
For how long?
Guess it depends on how bad the damage is.
How do you blush out ignorant?
What? Yes, you may.
Don't you go to this kind today? Will this kind fun?
No, there's not anyone. You turned in the other one. So you've got the other one is the one that just says energy at the top that I gave you yesterday. You may have already turned that one in too.
I think I turned both.
Okay. No, one of them was just a single sheet front and back. Okay. There you go. You are welcome. Let's get these passed out. Hannah.
Yeah, it's what that allows me to do is to post on Drive and I can move it. Okay.
I'm just asking.
I think I put it in as an 80. There you go. You're welcome. Okay, let's see. Okay, that's good. Let's see.